Okay, everyone. So welcome to this hands-on workshop about few-shot learning in production. I'm really excited that you're all joining us from all over the world. And this is work that was done in collaboration with researchers at Hugging Face, at Intel, and the UKP lab in Germany. And my name is Lewis. I'm an engineer in the open source team at Hugging Face. And I'll just briefly introduce my co-authors. I have here with me Moshe and Oren from Intel. Moshe, would you like to tell us a little bit about yourself?
Yeah, I'm Moshe Wasserbat. I'm leading the NLP team at Intel Lab. We're doing research, active research in efficiency in NLP. Thank you.
Hi, I'm Oren. I'm from the NLP team at Emergent AI Lab at Intel Labs. Have a lot of experience in efficient NLP.
Awesome. Thanks a lot, Moshe and Oren. So for everyone joining us on YouTube, just post your comments or questions and we'll answer them either as they arise or at the end. But in the meantime, if you want to kind of get a sense for what this is about, we have a few materials and we'll be posting the slides online later today. But basically, this is work that comes from a paper around using sentence transformers for few-shot text classification in a very kind of efficient way. And this is called SetFit, and there's a repository where you can visit in a blog post. But today we're going to be focusing on a kind of advanced technique of using this. So like sort of, what do you do when even with, a good model, you want to deploy this in some efficient way? So the kind of plan of attack for the workshop today is just to give a bit of an explanation about what SetFit is, how it works, and also to then talk about some of the sort of advanced techniques we looked at in our paper on compressing these models so that you can essentially deploy them on very small devices or at scale if you need to. We'll also do a hands-on demo showing you how we can do this in code on Colab. And as I said before, if you have any questions, just chuck them in the chat and we'll answer them on the fly or as we go. Okay, so let's dive in. So just for those who maybe are new to this field of few-shot learning, there's like many different kind of definitions of few-shot learning in the literature. But I think the most famous one really comes from the GPT-3 paper by OpenAI. And in that case, or in that paper, what they were sort of showing is that when you do language modeling, so when you do pre-training at scale, a large part of the corpus includes instructions where you might, for example, see something like translate English to French, some of these examples here. And then what you can do is you can get the model to kind of complete those examples, and then it kind of implicitly learns how to do, for example, translation, even though it's never explicitly trained on a translation task. And the reason it's called few-shot is because you provide a few of these kind of examples to sort of prime the model at inference time. And in the case of like large language models like GPT-3, this is typically called in-context learning because you're basically doing this at inference time based on the context. And in the original GPT-3 paper, they showed that if you look at the kind of accuracy over many different benchmarks in NLP, you see this kind of gradual trend as you scale the number of parameters in the model. And so, for example, the line here that we're interested in is this orange line for the few-shot. And so you can see that basically, when the language model is at the scale of like, say, like, I don't know, BERT or a bit larger, your performance or your average accuracy is around 35%. But as you scale up to like the 175 billion parameters of GPT-3, you roughly, kind of double that, or let's say 1.5 times that average accuracy. So this kind of suggests like a promising way of thinking about how do we deal with this common issue in machine learning as a whole, where you don't have many labeled examples. And maybe you would like to be able to just kind of provide the model at inference time, these examples, and then it just automatically is able to generate the completion, whether it's a translation or a class if you're doing classification. So this is exciting and, has led to a whole, slew of different, extensions to this idea and different ways of prompting the model and so on. But it does have kind of two sort of drawbacks. So the first one is that the performance of, these few shot approaches is very sensitive to the way that you prompt the model. So in this example here, you can see it's like translate English to French, and then there's a few examples of English to French. But it turns out if we kind of maybe, picked the wrong examples or, different examples, then we could get quite different performance in these completions. And so this has led to like a kind of sort of own field of what's called prompt engineering, where people devote a lot of time thinking about, okay, what are the ways we can kind of prompt these language models to boost the performance. And you may have seen on Twitter or other places where people do funny things like say, think step by step, and then simply telling the model to think step by step actually gets it to sort of break down the logic in how it's doing these completions. So that's the sort of first drawback, is this idea of having to always manually prompt the model and come up with clever prompts. And the second one is that, you can see in this plot that the performance really starts to take off at this like 175 billion parameter scale. And these kind of models are not the kind of models that you just have, lying under your bed and you just chuck them on your laptop. These are really, really big things which need, distributed infrastructure for inference. So although very promising, there are these kind of two main drawbacks. And to sort of deal with this, there have been a variety of techniques in the literature to sort of find ways that we can sort of maybe train smaller models in a more efficient way. And the current state of the art is a technique called TFew. And this technique uses a kind of clever idea where if we take a large language model, maybe we don't need to update all of the parameters when we're kind of doing fine tuning on our small labeled examples. Maybe what we can do is we can insert inside the network what are called adapter layers. And these adapter layers are basically just like small kind of like, feed forward networks. And basically then what we can do is we can just do fine tuning on the small labeled examples with these adapter layers. And this is a much more efficient way of kind of adjusting the sort of original model, whether it's GPT-3 or something else, to the sort of task at hand. And so TFew has this very nice property that it can do multitask training. So just using these adapter layers, you can basically train across many different tasks, whether it's classification tasks, token classification, translation, and so on. And what they show in this paper is that by using this kind of efficient adapter layers, they're able to get not only like very good accuracy compared to sort of the original GPT-3 models. So you can see on this plot that the sort of accuracy on the y-axis is better for TFew, but the actual number of flops that are needed for inference and training is significantly less. So you can see here that if I want to just do an inference using like the GPT-3 large, I'm going to need around 10 to the 15 flops for my inference, for my forward pass. And TFew is significantly more efficient. It's like 3 orders of magnitude more efficient than GPT-3. So this is currently the state of the art for kind of few-shot learning with reasonably large language models. But again, it has the kind of sort of issue that I mentioned before, that by being a kind of language model technique, it requires prompt engineering. So you still have to write your own prompts. And this, in our experience, is also kind of a little bit like labeling your own data. So you end up kind of doing a bit of double the work. And the other thing is that TFew, despite being, much more efficient than GPT-3, it still requires a relatively large model. So it's based on something called the T0 model, which is a model that came out from the Big Science collaboration. And this model is 11 billion parameters, which roughly translates into around 11 gigs of disk space. So again, deploying this model is not sort of like a super easy thing. It's much easier than GPT-3, but it is still nevertheless something that requires, some kind of specialized hardware. Okay, so let's check if there's any questions. So there's a question here from Amit who says, does TFew approach solve the latency issue? It only helps with training and few-shot learning. Yeah, so that's a great question from Amit. So in the TFU paper, they show that both for training and inference, they are significantly more efficient than models like GPT-3. And that's just primarily due to the fact that they're using a smaller model. So they're using a T0 model, which is around 10 times smaller than GPT-3. And for the training side, it's much more efficient just due to the nature of only having to essentially train a small number of the parameters of the total model. So great question. Okay, so I've sort of talked a little bit about sort of original GPT-3 approach and a more recent extension called TFU. So the kind of question that we asked ourselves in this collaboration is, all these advances are really exciting if you're like a researcher and you're interested in sort of generative models. But a very large part of like the day-to-day work as a data scientist in NLP is around kind of natural language understanding. So things like extracting embeddings or doing text classification. These are kind of very common tasks in industry. And the kind of question that we were interested in is can we do better than these kind of other methods? And it turns out the answer is yes. It involves a kind of very simple idea, which Moshe came up with. And we call this technique SetFit, which is a shorthand for sentence transformer fine-tuning. And the basic idea here is that sentence transformers, if you've never heard of them, they're essentially an extension or an adaptation of the kind of BERT-type models that you're familiar with. But they're essentially trained in a way where essentially you can do kind of like a Siamese network, which allows you to learn very, very good representations of text. And so sentence transformers kind of by themselves tend to produce much better embeddings than vanilla models like BERT. And the idea behind SetFit is, okay, we've got these very good representations from these models. Can we adapt them, essentially fine-tune them on a small number of labeled examples, and then use that kind of now fine-tuned sentence transformer to basically feed representations into a classifier or a classification head, and then generate the final predictions. So as you can see in this diagram, there are these two kind of stages of training. The first one is to adapt or fine-tune the sentence transformer on a small number of examples. And the way we do that uses a technique called contrastive learning, where you essentially sample, for example, examples that might be positive. So, this movie is great, and examples that are negative, which is like this movie sucks. And then contrastive learning will essentially adapt the sentence transformer to kind of cluster the embeddings further apart from each other, so that then when we do classification in the second stage, we've got a very good decision boundary to work with. And as I mentioned at the start, this is something that works very well for text classification. It also works very well for multilingual applications because there are a large number of multilingual sentence transformers that work well. And we're currently having a look at whether we can extend this to token classification, which is another very common task in industry. So as I was saying before, like the kind of idea of like, what this contrastive learning step is doing, if we sort of visualize it, the idea could be that, at the start, we might have some text, which is kind of categorized in terms of, maybe business, sport, politics, entertainment, tech. These could be like news articles. And although the diagram here is a universal sentence encoder, we can just imagine this is, sort of like our starting point with our sentence transformer. And so we've got some sort of, nice clusters, but we've got some overlap in various places. And then the idea is that once we do this contrastive learning, then we get essentially much tighter clustering, which then allows us to create very clean decision boundaries when we do classification on top of them. And so that's the kind of main idea behind SetFit, is essentially around generating good representations that then we can use to build classifiers. And just to give you a high-level summary, it works typically quite well with around 8 to 10 labeled examples per class. In some examples or some data sets that we studied, you can actually match the full fine-tuning on thousands of examples of like BERT or Roberta. just using 8 labeled examples. And it also works for any type of sentence transformer on the hub. So this is like a kind of big plus where you can just mix and match, pick a different checkpoint to see what you get. And you also don't have to write any prompts yourself. This is just using kind of standard like representation learning, where your inputs are just your text, and then the contrastive learning takes care of building these good representations. And as we'll see rather soon, it's very efficient. You can run this on one GPU in a matter of seconds, and on a standard CPU on a matter of minutes. So this really is a very big kind of contrast to, say, GPT-3 or even TFU, where you typically need at least one 80 gigabyte A100 to start with, or multiple multiple A100s if you want to run something like GPT-3 or Bloom. So this is really kind of helping us get closer to making few-shot learning accessible, sort of to the average practitioner. And to give you a kind of measure of where it stands relative to sort of these like fancier techniques, here's a plot from Raft, which is a benchmark that's commonly used for assessing the sort of performance of few-shot learning methods. And what you can see here are a variety of language models. So we have things, for example, like Bloom, we have GPT-3, we have these instruct models from OpenAI, which are kind of advanced, fine-tuned versions of GPT-3. There's models from Cohere, so kind of like the sort of who's who of large language models. And you can see that, the instruct models typically do best. And they have, parameters in the scales of like 100 billion. Whereas, SetFit or SetFit using a sort of Roberta model as a backbone typically gets kind of comparable performance, but is, 2.5 orders of magnitude smaller. So this is kind of this efficiency component that I was talking about at the start. So let me just take a couple of questions from the audience. There's one here from Emre, who's asking, does SetFit work well for multi-label text classification with open labels? And can different labels exist in new data? That's a really good question. So in our paper, we didn't do any benchmarking in the multi-label case. But one of my colleagues at Hugging Face, he extended this for the multi-label setting and found that, in general, you can get good performance provided that you don't have a huge amount of imbalance in the multi-label context. So my sort of general answer is like, try it out because you can run it in seconds. But as a general rule, it does work, but it depends on the data. Okay, let me see if there's any sort of last questions. Okay. Oh yeah, okay. And then maybe a common question here, which is something like just to explain is, what does per class mean? So basically when we are talking about, say, few-shot learning, often we say, okay, how many labeled examples do I have in my training set per class? So if I have, for example, like a sentiment analysis data set, I've got 2 classes, and the kind of few-shot regime of that might be, for example, having 8 examples that are positive and 8 examples that are negative. And we're going to see this kind of terminology per class, appear more and more as we go through the session. Good question. And last question here I'll take before we move on is, does it work for named entity recognition? So at the moment, we haven't kind of cracked that task, but we're looking into it. And if we do, then you'll find out soon enough. And yes, I'll be sharing the slides later on. So I'll put them in the YouTube video, which is actually being recorded. So once this goes to YouTube, I'll add the slides in the description. And I'll also show you later when we do the hands-on session where you can get the slides as well. Okay, so let's go. So everything I talked about so far was kind of just SetFit using typically a model that is roughly the size of BERT. So this is something that is a few hundred megabytes of disk space. And the question that you usually ask yourself when you say, okay, I've got something that works, is, now I want to deploy this to production, and maybe I have some constraints that I need to take into account. So the kind of obvious ones that come up is like, maybe you want to save money. So if you're able to kind of make your model smaller, you may find that you can use, one instance instead of 10. In the case of models like SetFit, you might be able to, for example, run them on very small, like edge devices, if you can compress them. The other one is that, by kind of shrinking your models, you might be able to then increase your throughput, because you can now, essentially fit, more queries or pass more queries per second, because your latency goes up, so it goes down. And the other one is, there are sometimes like some use cases, for example, if you're building, chatbots or things that have like low latency requirements, which, may be unlocked if you can show that, you can reduce the latency from, let's say, 20 milliseconds to say 1. So these are kind of like the three things that, people usually keep in mind when, going to production and asking, should we optimize these models? And there are these like three main techniques that are sort of commonly used, and Moshe and Aaron are kind of like world experts in all of these. And the ones that we're going to look at today is a technique called knowledge distillation and a technique called weight quantization. And there's a lot of interesting work that's actually been done by Intel around this idea called weight pruning, or how do you kind of sparsify the weights in a neural network. But we won't have time to go into that today. So we'll just have a look at these other two techniques, which are very common. And as we'll see, they can bring significant gains in your latencies. So I'll start by just giving a high-level description of knowledge distillation before handing over to Oren, and he can explain the sort of how we did it for SetFit specifically. But the basic idea of knowledge distillation is you have two models, and you have a model that's called the teacher. And this model is typically a large model, or it's a model that gets very good accuracy on the test set that you're interested in comparing. And this teacher model is typically a thing that is too big to put into production. So what you can do is you can take a smaller model, which is called a student, and then you can use essentially information from the teacher to kind of guide the training of the student, so that it basically mimics the predictions of this teacher, which is, gets good accuracy, but it is also able to kind of, benefit from what's been learned there, together with the labels of the original data, to get a student that would be basically better performant than if you just trained it by itself. And the way this works in this diagram is we've got some example, like the tacos were okay. The label here could be meh. And we feed both of these into the teacher and the student model. And, when we compute the loss, the thing that we typically optimize during training for classification tasks, this is usually like the cross entropy. So that's, one thing that we derive directly from the label. But the other thing that we can do is we can actually compare the distribution of the logits coming from the teacher and from the student. And so what you can see in this diagram is that, the teacher and the student will typically have different distributions, especially at the start when the student is basically just, randomly initialized. But we can compute something called the KL divergence, which is essentially a measure of like how different these two distributions are. And by kind of treating this as a loss, then we can optimize during training to essentially guide the student to mimic much closer the distribution of the teacher. And at the end of the day, we end up with something that typically then has similar performance to the teacher, but is also much smaller, and therefore can run faster. So this is like the kind of high-level view of knowledge distillation in the context of standard classification. But in SetFit, we took a slightly different approach, and I'll now let Oren explain how that worked.
Okay, thank you, Louis. So Louis showed a generic distillation setup, and now we're going to see the specific distillation setup that we used for SetFit. And the basic idea is, as in the generic distillation setup, is to train a small SetFit student model to mimic the larger SetFit teacher model. In the SetFit paper, we used a version of SetFit which is based on the MPNet sentence transformer. This is a model roughly of the size of BERT base, 110 million parameters. And this model produced very good results across all of our data sets. So in the distillation setup, we decided to use this model as a teacher model. And for the student model, we used a Paraphrase Mini-LM L3 sentence transformer, which is a sentence transformer that contains only 15 million parameters. So that's 7 times smaller than the teacher model. And this model is, of course, much more efficient and much more practical to deploy. So the first step of the distillation setup is to train the teacher. And in the paper, we trained the teacher using 16 labeled samples per class across all of our data sets. And the next step, if you look at the block diagram here, is to use unlabeled data and to use the teacher model to encode the data. So just to make it clear, in the training step of the teacher, we use those 16 labeled samples per class. This is the labeled data, but in the distillation setup, we only use unlabeled data. We don't use labeled data at all. So we run this unlabeled data through the teacher model, the sentence transformer of the teacher model. We encode the data and produce embeddings. So now we have embedding per sentence. And once we have it, we're producing the cosine similarity matrix that you see here. And this is essentially a matrix that represents the cosine similarity between the different pairs in the unlabeled data. So that would be the first step. And the next step, if you can click, Lewis. Oh, sorry. Go back. It didn't work.
Maybe I lost a slide.
Yeah.
So, okay. So maybe we can just explain it in words. And
okay, I explain it. Okay, and the next step will be to just generate or just randomly sample pairs from this unlabeled data, and then use those randomly sampled pairs in order to train the smaller SetFit model. It's the sentence transformer of the smaller SetFit model. And we're training the student by minimizing the loss between its cosine similarity, the cosine similarity in the output of the student sentence transformer, and the cosine similarity score produced by encoding the unlabeled data using the teacher. This cosine similarity here that we see in the cosine similarity matrix. So that's essentially the main step of training the student sentence transformer. And finally, the last step will be to train the classification head of the student by using the embeddings produced by the student and the logits produced by the teacher. Yeah, go ahead. Thank you. And now let's see some results. Here in this table, we see a comparison between SetFit MPNet, which is our teacher model with 110 million parameters, and the SetFit student, which is based on Mini-LM, which is only 15 million parameters. And in this test, we use 16 labeled samples per class for training the teacher. And for the distillation, we added all of the available training data and use it as unlabeled data. We just removed the labels from the training data and used it as unlabeled data. And if you look at the score here on the right, the rightmost column, this represents the average score across all of our 5 test data sets in the paper. And we can see that the SetFit student, which is 7 times smaller, just falls short of the SetFit teacher with only 2 points. And if we compare to TFU with 3 billion parameters, we see that the difference is only 3 points. So the bottom line here is that SetFit can be even more efficient when using smaller models in distillation setups.
Great, thanks. There's actually a question which is quite relevant here. So the first one is from Alexandra, which is, what is the benefit of using this unlabeled data if we kind of need these 16 labeled examples in the first place for the teacher? So maybe what's the intuition behind, using unlabeled data for the distillation step?
Yeah, and of course, if we were using just the label data directly on the SetFit student, the results would be much lower, and you will see it later. And the intuition is that the SetFit student mimics the output of the SetFit teacher, and the SetFit teacher is much larger, and the accuracy is much better. And the SetFit teacher actually produces, you can look at it as pseudo labels for the SetFit student. And we did see that when we use more and more unlabeled data, usually the results are improving.
Great. And there's another question which I think is kind of relevant, which is, as a concept, does knowledge distillation work if the sort of architecture of the teacher and the student are like significantly different? I have like my own kind of experience with this, but I'm curious, what's your experience, Aaron?
Yeah. Actually, I can also comment. We in the past we tried with BioSTM, and actually it's worked great. So yeah, I also recommend to try with BioSTM and smaller model. And there is some nice blogs that I can share with you in the comments later, how to do it with BioSTM. Or
Right. So you mean we had a transformer teacher model, and then we had a totally different student model like BioSTM, which is very different, and it worked.
Yeah, the only thing I've experienced before is if you are just using transformer models like, BERT, Roberta, and DeBerta and so on, if you try to like distill like, I don't know, Roberta into like BERT, you get like a kind of mismatch sometimes in the performance. Like it's like worse than sort of your intuition expects. And, the kind of usual explanation for this is that maybe like the representation spaces are like so different for these two models that, when you do the distillation, it doesn't quite transfer. But yeah, I definitely agree that on the LSTM side, this does work quite nicely.
Yeah, I can also add that's probably very much data set dependent. So for a simpler, more semantic lexical data set, it probably will work great. But if you have a very challenging data set, you need a larger model. So you will not be able to do it with BioSTM. You have to get a larger model or transform model. So it's very much dependent on the data set and the task in general.
Exactly. I'll take one more question before we move on. So why don't you use the predictions of the teacher model for training? So I guess the question is, why pick cosine similarity when, the conventional knowledge distillation setup is to like kind of look at the logits like I showed before and then compute the sort of difference in the logits itself.
Right, because we thought that SetFit, the body of the SetFit is sentence transformer, and the objective there is cosine similarity. So that's why we wanted to mimic the cosine similarity of the teacher. But in the second step, we do have a classification head in SetFit. So in the second step, we do use the predictions of the teacher to train the classification head of the student model. Yeah, the second step. So we use both.
Great. So then now take a look. Okay, so we've looked at like knowledge distillation, and we're going to show you some code where you'll see this in action. But the last thing we want to sort of mention before diving into some examples is this other very common technique that's used for optimizing models called quantization. And the kind of basic idea of quantization is that typically the parameters of transformer models, whether they're sentence transformers or else, are typically like 32-bit floating point. So this means that every activation and every weight basically has like a kind of range of values on 32 bits. But it turns out that if you look at the distributions in the layers of your network, they often don't take these extremely large ranges. And so you don't actually need that much kind of information to kind of capture the salient features of the model. So if you could find a way to essentially map the range of values from 32-bit to some smaller range, this would effectively use less memory, and it will also increase your speed, because when you do matrix multiplication with smaller amount of precision, you get some speed up if your CPU instruction set supports it. So what you can see in this example here is this is kind of like the sort of distribution of parameters in one of the layers of BERT. And you can imagine, you can see here that the range is only between, minus like 0.2 and 0.2. So what we could do is we could kind of convert all of these values into 8-bit integer. And this has the kind of effect of like discretizing the distribution somewhat. And the way this works in practice is you sort of take your original real value, your 32-bit, you divide it by some scale factor, and then you have to add this other constant called a 0 point, which just ensures that, the 0 in 32-bit aligns with the 0 of 8-bit. And so you can just think of this as just a way of just, mapping all of the numbers in your model into some smaller kind of precision. And as you may expect, there will typically be, some loss in accuracy. That's kind of like the general trade-off that you face. So as you go to lower and lower precision, you typically face a bigger penalty in accuracy. And there are many different frameworks for essentially doing this quantization technique. So you may have heard of things like Onyx Runtime. Even PyTorch natively supports quantization. But what we're going to use today is a pretty nifty open source library from Intel called the Intel Neural Compressor. And this essentially is an open source library that kind of encapsulates many of these sort of other frameworks. So it's kind of compatible with Onyx Runtime. It's compatible with Optimum, which is a library we have at Hugging Face for optimizing transformers. And it has like some nice features around quantization, where it basically has like a tuner that tries to figure out kind of what are the optimal parts of the model to quantize so that you minimize the amount of degradation from quantization. And this is quite different from, say, PyTorch, where natively PyTorch will just kind of quantize whatever layers that you specify, and you sort of lose a little bit of that kind of finding the optimal amount of parameters to quantize. So we'll see this in action shortly. And the kind of basic architecture of this library is that you're trying to build a bridge between like deep learning models and hardware backends. And so you can imagine that for most people, the transition is train a model in PyTorch or TensorFlow and then deploy it somehow. And depending on the hardware, you might find that just using native PyTorch isn't going to cut it. So you typically convert PyTorch into some other format, whether it's ONNX or TorchScript or something, and then that's the thing that you then deploy on a specific backend. And the sort of Intel Neural Compressor provides this kind of bridge, starting from a model and then having support for different kinds of frameworks. So whether it's just like Hugging Face transformers or just PyTorch models. And then inside you have all these different, say, compression algorithms and tuning strategies to do that conversion of taking your model and making it, faster. And then at the very end, you can have a target for a sort of, dedicated backend. So, are you running on a specific type of CPU? Are you running on GPUs and so on? So we'll see this in action very shortly. But let me just see if there's any kind of last questions before we jump into the code. So let's see. Yeah, so here's something that we'll see shortly, which is, I've quantized a model. Now can I do distillation to make it faster and smaller? So I think the answer is maybe yes, but doing it the other way around is probably better. So first distill the model. So you're doing everything in full precision, and generally training models in full precision is more stable. And then you can quantize it to get that final boost. And we'll see that very shortly. Okay, so let's jump into some code. Showing slides is nice, but let's see it in action. So basically, if you go to Hugging Face on GitHub, we have a repository called workshops. And in this repository, you can go to the Fuchsia Learning in Production folder. And here we have a link to the slides. So if you click on this, this will take you to the slides that we just showed today. And you can also click on this notebook here called SetFit Optimization. And this has a little button for opening Colab, which you can click on. And then this will now, spin up the notebook in Colab. and you can then switch, your your runtime to GPU, and then you can now run everything as you go. I'm going to run this on my own GPU just because it's a little bit more stable than Colab. I'm not sure I trust Colab to always do everything I want. But basically, what this notebook is going to show you is how to use these two techniques we just covered. So we're going to first use knowledge distillation with the method Oren described to shrink the sort of teacher model into a small student. And then we're going to take that distilled model and we're going to then quantize it using the Intel neural compressor to sort of squeeze out the last bit of performance. And just to give you kind of rough rules of thumb, like it depends a lot on the model and stuff, but typically, you'll see a 2 to 4x reduction in size from knowledge distillation, and then another kind of additional 2x compression at the quantization step. And these numbers kind of vary, depending on the model and stuff, but that kind of gives you a rough idea that if you combine these two methods, you're able to kind of compress a model, maybe by as much as 10x, which again, translates potentially into, a 10x reduction in your kind of deployment costs. So there's a few things. You just have to install the dependencies, and I'm just going to turn off a bunch of warnings from transformers. So let's talk about, how are we going to compare the models that we train? So the sort of most common thing that you'll experience when you want to deploy models into production environments is there's kind of this sort of trade-off between the performance of the model. So kind of like, what is its accuracy, or, what are the metrics that are important for solving the task at hand? The other one is the latency. So kind of like how fast can your model deliver predictions? And then the third one is like memory. So kind of like essentially how much RAM or GPU memory does the model take? And that can be important if you're dealing with, very like small devices. Maybe you want to run the model actually, in your phone, or if you want to run, on very small instances, in a data center, so you can, save costs this way. So each one of these things is often in a little bit of tension because, if you try to optimize exclusively for latency, you may get a hit on the performance of the model, and vice versa. If you just optimize for model performance, you may end up having, large models. And so figuring out what is the best combination depends on your use case. But today we're just going to look at kind of the relative gains that can be had by sort of looking at these three dimensions. So the first thing I'm going to do is I'm going to create a performance benchmark, which will allow us to feed in a SetFit model, a data set, and a kind of name for, the type of model that we're dealing with. And this function or this class is going to compute the three things we talked about. So it's going to compute accuracy, it's going to compute the size of the model, and then it's going to also do a timing of the model so that we can measure the latency. And I won't go into all the details here. They're maybe not so interesting, but basically we just generate predictions from the model and compute metrics using the evaluate library from Hugging Face. And then to compute the size, we just look at the sort of state dictionary of the PyTorch model. And then for the latency calculation, we just basically loop over 100 examples of some query, and then we just compute the average latencies and the distribution from that. So if I run this cell, we've now got something that we can use to compare models. And what we will be focusing on today is a data set called AG News. So the AG News data set is a fairly popular one in NLP. And you can see here, it's essentially a data set of like news headlines or, snippets of news articles, which are then categorized into 4 different classes. I think it's like business, sport, politics or world, and then, technology. And so you can see here in this example, it's like Wall Street bears, blah, 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 something, short sellers, Wall Street, something. So, this is like something about maybe business. And then if we look at another example down below, I think we have one here. This is like more like a tech one. It's like, AOL to sell PCs to minorities and seniors, blah, blah, blah. So you get a sense that like, we've got text that has quite different kind of categories. And the kind of question is, can we train a classifier on this data set, but only using a very, very small amount of the labeled examples. And let me just check if there's any issues. I think this data set is quite large. It's like over 1 million news articles. And what we're going to try and do is see if we can, just use maybe 8 articles per each one of these 4 classes to train a classifier. So we've loaded a data set. And now what I'm going to do is I'm going to create a bunch of different training sets for the different things that we want to do. So the first thing I'm going to do is I'm going to create a split. I'm going to split my kind of full training set into 2 pieces. The first piece is going to be used for creating these few labeled examples that we'll use for training the teacher. And the second part I'm going to use as the sort of unlabeled data that we would use, for training the student with knowledge distillation. And you can kind of imagine that in many practical use cases, you will have maybe a few labeled examples, but you might have a pretty large number of unlabeled examples. And this is kind of true if you're in domains where domain expertise is kind of really important, right? You can imagine if I'm doing law, contract, classification, it's expensive to get lawyers to, manually go through and annotate my data. So I might have a few examples at the start of my project, and then I might have a whole, stack of contracts that haven't been labeled. And so this is what we're kind of simulating here, is a scenario where you start off, having just maybe 10 examples labeled, and then you want to see if you can use that to squeeze more performance on the unlabeled data. So this cell just basically samples these kind of few shot examples from the training set, and we can have a look here. We've now got 32 examples for training the teacher, and the reason it's 32 is we're going to basically take 8 examples per class. We've got 4 classes, and if I remember my math, 8 by 4 is 32. And similarly, if we look at the student, we've now got these 1,000 examples, and we're not going to use the label of this at all. We're just going to use the raw text for distillation. And then for the test data set, here we're using the full thing, which is, relatively large, but this is just as a way of measuring, how well the models are. And if we had less, it would also be fine. So the way this works when you train a standard SetFit model is first we're going to load a pre-trained sentence transformer from the hub. And this is essentially going to download the weights from the hub, and then it's going to attach a classification head on top of this model, which is the thing that we need to train in the second stage of SetFit. And then we're going to feed that model into a trainer. We provide just the model and the training set. And there's a bunch of default parameters that we're using, which basically tend to work out of the box. We're going to train the model, and then we're going to feed the resulting model into this performance benchmark class to compute some metrics. So I'm just going to run this now, and this should give us a sense of how fast SetFit is. So you can see here, it's taking maybe 15 seconds. I'm running just on one GPU. And this is, essentially doing that contrastive learning step we spoke about on these, 32 labeled examples to essentially kind of tune the sentence transformer, and then we just do a kind of logistic regression on the top of that. And what you can see is that the model size is around 400 megabytes. It gets an accuracy of around 82%, and the sort of latency is around 11 seconds running on my device. And so this is kind of nice, 82% accuracy on this data set with just 8 labeled examples per class is quite good. And so at this point, right, you might say, okay, I'm done. I could just deploy this and, call it a day. But, the thing that you typically ask yourself is okay, could I use a smaller model to get similar performance? So what we're going to do next is we're going to now take a different sentence transformer. This is the mini LM transformer that Oren was mentioning. And this is going to be, it's around 4 times smaller, or even more, 7 times smaller than the original model. We're going to train it in the exact same way, and then we're going to compute the metrics, and we'll just get a sense of how much the performance is impacted by using the smaller model. And so as you can see, it's 66 megabytes. The performance has dropped almost, 7%, sorry. And the latency has also gone down, which is good. So we've got something that is faster, but it's got, a big hit in accuracy. And we can actually visualize that using this function here, where we can see that, the original sort of NPNet model has a latency of around 11 seconds and an accuracy of 82%. But the sort of student model has, much faster latency, but has suffered this performance hit. And so the kind of thing we want to show now is that if we use knowledge distillation to essentially train the same mini-LM model, but if we combine it with the embeddings from the teacher, we can ultimately end up with something which is, hopefully as performant. So there's a question here which is kind of maybe relevant for what we're about to do, which is, in this case, I'm just using unlabeled data, which is kind of the same domain, so to speak. What happens if we had just completely random, text news? And yeah, that's kind of an interesting question, Oren. I guess, do you have any sort of experience here? Like if we took, the sort of 16 labeled examples or whatever for the teacher to train on AG News, and then we had just random news articles, do you think the distillation would also work, or is it important that it kind of has the same kind of distribution to start off with?
I think that the same distribution helps here. Mm-hmm. Yeah, and do you mean from take data from completely different domains here?
Yeah, I think what Mohammed's asking is, like if we maybe just had news articles from like, a different place, maybe we have a bunch of news articles from Reuters, and then, I don't know, maybe the news articles are from BBC or something, or, Reddit or whatever.
Yeah, I think it depends on the semantic relatedness, right, in the unlabeled data. Yeah, exactly. But it's definitely interesting to test.
Yeah, I guess the main thing I'll say to Mohammed is that you'll see in a second, this is quite fast to experiment with. So you can always just run the experiments very quickly and check for yourself. And there's a question from Ankush about will this notebook be available? Yeah, it's available already. So if you go to Hugging Face Workshops, you click on the Fuchsia Learning and Production folder in the SetFit optimization, you can already run it. Okay, so this is like a starting point. We want to make this mini-LM model better in accuracy. And so now we're going to use a distillation SetFit trainer, which again, we load now the same mini-LM model. But what we're going to do is we're going to feed into this distillation trainer the teacher model. We're going to feed the student, and we're also going to provide this unlabeled data for the trainer to work on this kind of, semantic embedding comparison. And so if we run this, it's, very similar code to what we saw before of training the standard SetFit models. But now it takes, a little bit longer because now we're kind of, doing this kind of unlabeled data comparison of the embeddings between the student and the teacher. But nevertheless, this is only going to take roughly, a minute on my GPU, using these 1,000 unlabeled examples. And so, if you had more unlabeled data, it's roughly going to scale linearly. So again, these are things that kind of show that, even though you're using like a lot more data to train the model, you're not paying like a very heavy penalty. Whereas, some of the other sort of techniques that people use for like few shot learning and distillation, they often use like generative models like, GPT-2, which have to like do a lot of heavy lifting to kind of do this kind of compression step. So this should run in around another 10 seconds. And then we should see what happens when we get to the end of this plot. So there's a question here while it's running. Oh no. Can we use distillation for semantic search? I think the answer is yes. You can do it for getting good embeddings. And if you have more questions, you can open an issue on the SetFit repo. But what we see here is now we've got a model, which is the mini LM model of 66 meg, but it's now basically got the 82% accuracy that we started with from the teacher, but has the benefit now of being, roughly 3 times faster. So this is quite cool, right? We're seeing that we can shrink the model significantly in latency, but we get a significant boost over just training the student model on the few labeled examples we have. So here I'm going to now push this model to the hub. And so if we run this push to hub cell, it will basically push a model to the hub, which contains a bunch of files. So you'll have all the things that you need to basically, deploy it, run inference with it. And what I want to show you now is, like, at this stage, you could deploy this on your own kind of infrastructure, whatever you want. But I want to show you a kind of nice technique of how we can deploy this on Inference Endpoints. So Inference Endpoints is a service that Hugging Face offers to kind of deploy your models on the hub on like a fully managed kind of cloud infrastructure. But it also has the advantage that you can do this in a secure way. So you don't, have to worry about, all the kind of issues of having like hosted models on some external thing. You can really run this, privately through your own cloud. And so to give you a sense of like what it takes to deploy a model, the way this works is you basically provide the repository that you're dealing with. So here I've got a SetFit model, and it's the mini LM distilled one. And then you can select the cloud provider that you want to deploy on. And so at the moment we support AWS and Azure. And so I'm just going to pick AWS because, why not? And I'm going to pick Ireland because I'm in Switzerland. So let's make it close to where I live. And here you can select a few of like the sort of different hardware that is available, in this region for this cloud provider. And since we've now got this relatively small model, I can actually pick essentially the smallest available CPU, which is one of these Intel Ice Lake CPUs with 2 gig of RAM. And then I'm going to just specify a few things if I want to about the advanced configuration. This is a task which is actually for text classification. So let's do it here. I can also specify things like auto scaling and stuff like that. But for that, I think we can leave that out. And I can also change the framework if I want. But this is automatically detected that this was a PyTorch model. And then at the very end, you can also specify whether you want this to be like fully private using, something like these private link connections that cloud providers have. But since this model has been trained on, public data, I'm just going to make it public. And so when I hit create endpoint, this will now essentially start building a container. And then once that container is deployed and built, we can then actually, query this and, use it in applications downstream. So building the container takes a few minutes. So while that's happening, I'll just show you one that I built earlier. So here's one that I deployed earlier. And now we've got something that is running, and we can now provide examples just to test it out. So we can say like, okay, in today's news, Morocco trashed France in the World Cup. I guess we'll see. And that has identified it, indeed it's about sport. And, we can think of other things like, okay, I don't know, Intel releases the biggest language model on CPUs or something. And then fingers crossed, this is now about tech. So you kind of get a sense that, the model is moderately good at, classifying these kind of, simple things. And then, when this is deployed, you can also use, curl to run this. So if I have, my, I want to put this in like a request thing, I can then feed that into my terminal. And now, I've fed in this text, and now I've got the label, the score, and so on. So this kind of shows you in a space of a couple of minutes how you can take, a model that's already on the hub, and then you can deploy it on your own kind of selection of hardware. And that's, one thing that I find quite nice, because a lot of the time, if you might want to experiment as a developer and say, okay, maybe it's better that I use a GPU for this type of thing, or a CPU. And when you're dealing a lot with like external, inference providers, you don't quite have that flexibility. Now, the one caveat here I want to mention is that Inference Endpoints supports several frameworks out of the box. So it supports transformers out of the box. But SetFit is kind of, its own library, right? So it's not something that is natively supported in Inference Endpoints. So what I actually did to make this work is I implemented something called a custom handler. And this custom handler is essentially a class that just tells Inference Endpoints, what is the forward pass, given a payload, what is the output? And so here, this endpoint handler just basically loads my SetFit model. It defines the label mapping. And then in the forward pass, I receive some payload. And then I just feed that payload through the model and then return an array of the labels. So this, again, is something that is quite neat, because you can basically write, you can deploy arbitrary models. I can deploy, random PyTorch models. I can deploy random TensorFlow models. And as long as I sort of implement this kind of endpoint handler, I'm able to kind of control specifically, how the inference is done, which is another kind of nice part of flexibility that you don't quite get with, external API providers. Okay, so that's a super quick example of Inference Endpoints. I'll take some questions later if there are any. But now that we've seen, how to do distillation, I want to just wrap up by diving into this last kind of thing. Can we squeeze even more performance out of this distilled model? So the way we're going to do this with the Intel Neural Compressor is the Neural Compressor can apply quantization on different sort of frameworks. So you can do basically quantization on sort of like the native PyTorch model or TensorFlow. But it turns out that if you want to get kind of like the best kind of compression, it's good if we kind of take an intermediate step where we convert the model to ONNX, and then we're going to compress the ONNX model, and that's the thing that will then run. So the way that we can convert the model to ONNX is we're going to use something called Optimum, which is a library we have at Hugging Face for basically wrapping all of these ONNX models and running them through ONNX runtime. And so now I'm going to load the model that we've trained using what's called a feature extraction model. So this is basically just the body of the model. This is like the sentence transformer. And then I'm just going to save this to disk, so that now we've got something called, let's see, we've got the tokenizer, and we also should have now in this folder an ONNX model. So I'm not going to go into tons of details about what ONNX is, but you can just think of it as a way of kind of capturing your the structure of or the architecture of your model in terms of a graph, where all the nodes in the graph represent operators. So you might have nodes where you've got things for like matrix multiplication. You'll have nodes for like the activations and so on. And once you've got that graph, you can then do tricks like you can combine nodes. You can kind of apply quantization, and that's what we're going to use with Intel Neural Compressor. So because we have an ONNX model now, it's not like PyTorch where we can just run it using like PyTorch modules. What we actually need to do is create a kind of ONNX version of the SetFit model that we used previously in all the training. And so this is like, it looks a little bit complicated, but it's not too much. We just have to implement something which takes an ONNX model, takes the tokenizer and the model head that we trained from the student, and then we just implement a predict function, which is going to basically define how do we do inference with ONNX and ONNX runtime. And then we have a call method, which will then, just essentially wrap that predict method. And so now if we instantiate one of these Onyx models, we can basically feed in some text examples. So here you can see, here we've got a couple of examples from the test set, and then this will now generate, predicted labels identical or very similar to, the original PyTorch model that we had. So we've got now an Onyx version of our SetFit model. Let's now, quantize this model. So the way this works in Intel Neural Compressor is we have to define a couple of pieces. So the first thing we need to define is essentially an evaluation function, which basically will compute the accuracy of the model at a given step in this tuning regime. So basically the neural compressor will try to figure out which kind of parts of this Onyx graph should be quantized, to get the best kind of accuracy. And this evaluation function is just simply going to take in the model at some point, compute the predictions, and then finally return the accuracy. So the details here are maybe not super exciting and interesting, but basically we're just computing accuracy from the Onyx model. And so I'll define that. The other thing we need to define is essentially a YAML file, which specifies kind of what framework we want to use for quantization. So here we're using, Onyx runtime. We're using CPU for inference, and we're specifying that this is now dynamic quantization, sort of post-training. And we set some threshold on like, okay, when should I terminate the tuning? And my kind of criteria is that, I basically don't want my accuracy to drop more than, 0.01 relative to my baseline. So we're going to save that in this YAML file. And now the last step is to basically define this quantization object from the neural compressor. And this quantization object will now be essentially the thing that will run the tuning. So here I'm basically feeding the Onyx model. I'm feeding this evaluation function, and now I'm going to run the quantizer. And what this is doing is this is basically running this evaluation function to get a measure of the accuracy, applying some quantization to the Onyx graph, and then running the evaluation again. And it does this several times so that, at the end you say, okay, this was the best kind of set of, quantized operations I could find. So this takes like around a minute or so to run. So while it's going, I'll think if there are some questions. So here's a question from Javier about inference endpoints. So is it planned or available a pay-by-use plan for endpoints? Currently, you only pay by hour. That's a great question. As far as I know, there are discussions of kind of thinking about, what might something like serverless work look like for inference endpoints. But if you want to know specifically, I recommend just getting in touch with Philip Schmid or just sending an email to Hugging Face, and they'll be able to answer that. Let's see, another question. What amount of per class samples would be needed for 100 plus classes? Yeah, that's a great question. So I think in the extreme, label classification context, what we've seen is that the problem here is typically you'll have like a lot of sparsity. So you'll have, some of the classes are like densely populated, but then you'll have some very rare ones. And I don't have like a kind of, golden rule of thumb for what that should be. But some experiments people have done in the community show that, even if you're only able to have around 8 to 10 labeled examples across these classes, you can get like a very strong baseline. So it may be not something that you can, use in production, but at least it's something that you can, build from. Okay, so this is now run the Intel Neural Compressor, and you can see that it says, okay, we started off with a baseline in the full precision model of 82%. And then at the end, we found the best kind of compressed model is, 81.9%. And now we've got something which has been kind of quantized into this 8-bit integer precision. And so what I'm going to do now is I'm going to save that to disk as model quantized.onyx. And now what I'm going to do to just wrap things up is basically run the performance benchmark, But now I need to just define how do I compute the size of the model, because previously I was using PyTorch to do that. And so here I have to actually just look at the size of the model on disk. And then to compute the accuracy, I now need to use a slightly different logic, because in the PyTorch case, we were able to use the PyTorch trainer. But these again are just some details you can look at after this workshop. So I'm going to basically load first the Onyx model, and then I'm going to feed it into my Onyx SetFit model. And now we're going to run this inference benchmark. And so what you can see here is that this is now compressed the model from 66 megabytes, which was the distilled version, into 17 megabytes, which is quite impressive. That's like a factor of 3.5. And for a lot of like quantization techniques, typically you'll only see like a 2x compression natively. But because the Intel Neural Compressor does this kind of tuning directly on the Onyx graph, it's able to get like a very efficient representation. And so we'll soon see what the effect is on accuracy and on the latency. Let's give it a second. So the accuracy indeed has only gone down to 81.9. And here you can see the latency is quite impressive. This is now hitting the 1 millisecond latency range. And we've now been able to, relative to where we started from, right? We started off here with this MPNet model. And by adding distillation and quantization, you go roughly from, 11 milliseconds down to roughly 1. So that's like a factor of 10 reduction, in your latency. So when I saw this, I was like, well, this is cool, because usually I'm only used to seeing like 2x gains, and Intel Neural Compressor is quite impressive in this respect. So maybe the last thing to mention is like, why do all this stuff? Like we've been talking about like, optimizing for, latency and throughput and stuff. But a kind of like bottom line comparison to show you what I'm talking about is, if you take the state of the art for few shot learning today, which is the TFew model, if you want to deploy this into production, you're going to need to use, for example, an inference endpoint, which is an A100 with 80 gigabytes of GPU memory. And so the hourly rate for this is around $6.50. But by comparison, we can deploy this compressed SetFit model on, the very smallest CPU that we found, which was, this one vCPU with 2 gigabytes of RAM. And so you can see it's over 100x reduction in price. And I think that's like, if you're working in industry, these are the things that I sort of, are important to take away, where, if you only read Twitter and stuff, you might get the impression that like, large language models are like taking over the world. But there's a kind of deeper story here, which is like, if you actually want to use them in your job, the cost of deploying them is an important consideration. And, what I hope we've shown you today is that a technique like SetFit, for the specific use case of text classification, which happens to be, one of the most common ones, is a way to both iterate very fast in your development, because you saw that we could train all of these models in seconds. But then for the deployment, you're able to, significantly reduce costs. So that kind of wraps up what we wanted to show you today. We covered a huge amount of stuff, so I'm pretty sure, like, your mind is exploding, and it's time to now, watch some football. But if you want to, again, dive into the details, you can check out the workshops repo on GitHub, and then the SetFit optimization notebook. And maybe what we can do now is take a few questions from the chat. So the first question is TFew also quantized in this comparison? No, so that's a good point. In this comparison, I'm just comparing just TFew unquantized. Probably one could maybe, apply some techniques like distillation and quantization. And then you would, the relative comparison would be lower. But generally speaking, just doing, training and stuff, all those things with large models requires more hardware. So you need like, to factor in those kind of additional costs. So let's see, what kind of questions do we have? Yeah, so another question is from Javier is the model head a PyTorch in a module? So in the examples I showed today, it's actually simpler than that. It's just a SetFit logistic regressor. But in the SetFit library itself, we do provide an implementation that's pure PyTorch. So if you want to just stay, fully in the PyTorch realm, you can do that, and that works, just as well. And let's see what other questions we have here. Oh yeah, so there was a question from Emre about the latency numbers. So the ones that I showed at the end with the quantized model were on CPU. The ones previously were actually on GPU, but I did a comparison internally just to see, what the difference was, and it was kind of negligible for this particular example. So all of these plots that I showed here, they basically look identical if we run everything on CPU. Let's see. Just checking through the questions. Yeah, maybe this is a question for like Moshe or Oren. So, could you like pre-compute embeddings for SetFit for inference? So, maybe you've got a database of documents and you want to classify the text based on sort of a question appended to the docs. I guess the answer is yes, but I'm just curious, what do you think?
What do you think, Moshe?
I'm sure I understand the questions, but
Yes, I think the way we could think about it is like, in some cases, I think when people are doing things like, semantic search, they often like pre-compute embeddings and then store them on like an index that lets you do like fast lookup, like FICE or something.
Yeah.
And I guess the question here is asking, would a similar technique help for SetFit? My kind of hunch is like one could do that, but probably it doesn't bring you much gain because, the model is so fast that you don't really need to do any of this like pre-computing.
I think if it's related to semantic search, I think you can apply the same methods also for semantic search and actually benefit from distillation the same way that we show for text classification. So I think it would be interesting to validate on semantic search task. I think it should work the same. You can do it in offline. You can have a smaller sentence transformer model and apply it as for semantic search. Yeah, I think this is a nice approach to optimize semantic search in production, basically, not just text classification. Yeah,
Yep.
sure.
Yep. Totally agree.
Yeah.
And then there's, let's see if I'm looking through the comments. So
I would just mention that what you see here in the graph, the smallest model is 25x smaller than the teacher. And you see its comparable performance. So in terms of not just latency, but also model size is 25x compared to the teacher. So yeah, it's quite sufficient for production.
Okay, so here's an interesting one just to wrap up the session is sort of like, could you have like a human in the loop kind of combination? So you're using SetFit to kind of bootstrap your labeling, and then, as you collect more labels, you can then sort of update the model. My understanding is that this is possible. There's a library called Argia, which is a kind of labeling tool. And I think, as far as I know, they have a nice tutorial where they use SetFit to kind of do this like active learning process. But indeed, I think Moshe and Oren, you've also done experiments using like SetFit to generate like pseudo labels, right? Like where you you train on a small number of examples, and then you can kind of generate kind of like weak labels. Or maybe I'm misremembering the experiments.
Yeah, maybe something that is related. What I did is first have a few shots with 8 samples and create a new model, and then use this model in a tandem way to get more data, to continue to do fewer shot learning. So it's possible, you know, to have kind of a few steps that you, in each step, you create a new fine-tuned model and then use this model for the next step with more data. So really possible, and it's actually can boost your performance. You can add more data if you and start with a fine-tuned model already. Yeah. So it's a good approach, definitely.
Yeah. Another point could be self-supervised learning, right? When you start off with those 8 labeled samples per class, and then classify unlabeled data, and then choose the best data and retrain the model iteratively.
Yep.
That's something that we're also into and we want to examine.
Okay, cool. So I think with that, let's call it a night. I want to thank everyone for joining. I'll very quickly put a link in the chat to the notebooks. So for everyone who wants to run this, during the match. But yeah, again, thank you very much to everyone for joining and for the very interesting questions. The recording will be available on YouTube shortly after the session. If you don't see it, you can always just get in touch with me. I'm pretty easy to find. There's only one Lewis Tunstall in the world, I think. And if you find me, you'll find me on Twitter. So yeah, thanks again, and have a good evening. Bye, everyone.
Thank you. Good evening.
Thank you, Luis.
Bye.
Bye.